Good afternoon, class. In today's video, what I'd like to do is go over moment of inertia. Now, this is the analog of regular inertia, which in linear motion we call mass. So this one is kind of the same thing, but there are some big differences because it works the same way in terms of physically. It's a resistance to a change in motion. So if you've got something that is rotating, it will want to keep rotating. If it's not rotating, it will resist being rotated. There will always be that, and which is the same thing with linear motion. If you got an object in motion, it will stay in motion unless acted upon by an outside force, or if it is at rest, it will stay at rest unless acted upon by an outside force. So that is the same in terms of how physically we would deal with that. However, as you can see, there's a lot to say about moments of inertia. It's a very complex topic. And that's why, like I said in my introductory video, I invented this geometric factor here. This star doesn't actually exist. And that's why I didn't use any letter of the alphabet or any Greek symbol, because I knew that if I did, it would get confusing down the road when you're in another class. Maybe you're learning physics from a textbook, or you're reading something about physics, and you'll see that there is actually nothing over here. So if I used a letter, it would confuse you. But if I used a symbol like star, which no sane scientist would ever use, then I feel like I'm justified in using it because at least you all know it's something that I, Mr. Achiu, have invented and no one else has. And no one else uses it, in fact, outside of literally my class. So take that for what it's worth, but I thought I'd use it as the opportunity to point out a few things. So keep in mind that the equation for moment of inertia is I equals star mr squared. What is that star, you might ask? That's a good question, and that's where all the stuff that I wrote in blue comes in. So that geometric factor, there are several examples of that, and I thought I'd bring them out as little props. So you have something like this. It is some wipes that I have in my class, and this represents the solid disk rotated around the symmetry axis. So for example, if I had a disk like this, solid disk, and I rotated it like this, that would be this moment of inertia. I would be looking up this factor, and that factor is 1/2. Now notice if I had the same thing, but it was shaped like a hoop, like this roll of tape here, that changes, and especially if I'm rotating it around the symmetry axis, that changes it because now it's twice. The geometric factor is twice as big. It's now I equals 1 times mr squared. And you can compare. The r value here and here are not the same, but they're fairly close. So if I were to rotate this technically is twice as hard to rotate as this one to rotate. So I thought I'd show that to showcase how you can have differences in the geometric factor. Simply, nothing else is different really. The masses are generally the same. The radius is a little bit different, but good enough for this example. So I thought, you take a look at it, and yet this geometric factor will have a big difference. So let's go on to the other one where I told you I would bring out the ruler again, right? My trusty meter stick. So this meter stick represents a rod, and rotating it around the center. So I grab it right about here in the center, and then if I rotate it, as you can see, I can move that fairly fast. I'm not moving my hand very fast, but this rod is actually rotating quite quickly, which means there is less resistance to me rotating it like so. However, let's say I put, so I'll hold it like this, but I'll put it over here now. So let's say I hold it at the end. Right now, it's going to be a rod around the edge. So if you want to pause the video and look, that is 1/3 ml squared. The rod around the center, 1/12 ml squared. So again, as you can see here to here, very easy. However, from here to here, same motion from this hand, but did you notice that this part was a lot slower? And the reason for that, right, even if no matter how fast I try to move it, is because of that geometric factor. this is the same. This is the same object. It is still, the mass is the same, the length is the same. It's still 1 meter, just like always. But because I changed where I held it, whether here or here, it actually makes a big difference when it comes to how well this thing rotates, like this. One application for this is if you ever used it as a baseball player and you ever were told to choke up on the bat, that's why. Because what you're doing when you're here, you're swinging it, the swing is actually a lot slower because you're holding the bat at the edge like this. You're increasing the geometric factor basically by a factor of 4. So they tell you to choke up on it a little bit so that when you swing it, it actually goes a lot faster. Sure, you don't have as much reach. Maybe if the ball curves out, you know, I'm not even going to try and guess what kind of pitch that would be because I'm sure all of you baseball players are definitely going to get upset with me if I said that. So I won't even try whether it's like a slider or a curveball or whichever one it is. In fact, comment that in the comment below. What kind of pitch is it that would be you would have a hard time swinging at if your bat was a little bit shorter because you choked up on it? So with that, that's the geometric factor. That was a whole major part of this video because that's the part that's really confusing and it's something that you have to know. This is not an exhaustive list, by the way. This is all that I had props for. There are like solid spheres like cue balls or pool balls and the earth. Those are solid spheres. You could have all kinds of other shapes and they're all listed down and you can just look them up. So that's just something that you have to do in order to figure out what this geometric factor is. But it's a number. It's a constant that you can just write down and just figure out. Will the mass of the object change? No, there's not really anything more to say about that one, so I can just leave the mass of the object as is, just the way we did in linear motion. However, this radius is going to be very different, right? Because this is the distance from the fulcrum to the edge of the object. So I'll start with this roll of tape right now. The distance from the fulcrum, so if I'm rotating it, it would be from the center of this tape all the way to the edge. So basically the radius, kind of like the one I showed you in my linear motion and my rotational motion video, you know, just in the previous one. So there's the radius over here. That is this R value. Or if I were to use my solid sphere like this, it would be from here all the way to here, or from here to here. So that is that R. Now, you'll notice that there is a difference when it comes to the rod, okay? Because for the rod like this, what you need to do is you can't measure from where you grab it to the end. It has to be it's just the entire length of the rod itself. So that is something that you do need to consider. Also, you know, so that's why that's something to consider and to keep in mind because this is different. That L value is different for rods and it is not the same for other objects. So you do have to be careful about that when you're looking up the moment of inertia for certain objects. If there is ever a need for like a special object or a special type of object with a very weird moment of inertia, I will tell you that one. So don't worry about that one. One of the things that I do want to point out too is this word fulcrum. This is another way of saying pivot point. So you could, and you have several of these on your body, so I thought I'd use my own arm as an example. As you can see, this is my elbow. So if I were to rotate my arm around this is where the pivot point is. And you can tell because if you see my finger here, it doesn't move when I rotate this. There's no rotational motion. Whereas over here, there is a rotational motion as I move where my finger is, right? My finger goes through some angle. So here, there is nothing. So that's why this point is the fulcrum or the pivot point. So you have that. There's a pivot point here on your shoulder because you can rotate around your shoulder. On your hand, basically at every knuckle, anytime you can rotate around something like this, that's a fulcrum. That's a pivot point. Other examples of this, if you've ever been to a park with a seesaw, the middle of that seesaw is the fulcrum. So those are some ways to think about fulcrums and this distance from it, because those things are gonna get a little bit counterintuitive, maybe not counterintuitive, but just they're not intuitive in terms of how you picture that in your everyday life. I'm sure some of you who have watched the Olympics have seen certain figure skaters and certain athletes perform incredible feats of athleticism, and they've utilized this fulcrum all the time. In fact, you'll even see it in many martial arts videos as well. So this concludes this video on moment of inertia. Next time I'm going to go over angular momentum. So good luck in your studies, and I'll see you in the next video.